Schroeder's theorem. If A is a bounded operator from X to Y, then A is compact if and only if A star is compact. Proof. Assume A is a compact operator and let Yn star be a sequence in ball Y star. It needs to be shown that A star Yn star has a norm convergent subsequence. Then if that can be proved, then A would be a compact operator. A star would be a compact operator. So by Aloglu's theorem, there is a Y star in ball Y star and the subsequence Y stars n sub k such that Ynk star goes to Y star in weak star topology. So we are going to prove that A star Ynk star minus A star Y star norm goes to 0. If we can prove this, that means this sequence A star Yn star has a cluster point. So since that is an arbitrary sequence in A star of the ball, that would mean A star of the ball has a compact closure. Actually, if we can prove this, then A star of the ball is compact, not only has a compact closure. Oh, in the compact closure, yeah. Okay. So so actually, yeah. All right. So we are going to prove this norm goes to 0. If norm goes to 0, that means this sequence has a cluster point in A star of the ball. So A star of the ball is compact. So that epsilon is greater than 0. Then there are Y1 through Ym in Y such that A ball of X is contained in the union J from 1 to M. Y is equipped Y, norm Y minus Yj less than epsilon. So yeah. So the idea is that we want to show this norm goes to 0. And this is true if and only if when this functional applied to when this functional applied to x in the ball of script x, we have infinite many points. So for each one, we would have that functional, this applied to the functional would go to 0 for each one vector. But since we have infinite many vector in the ball, we can not, in general, we cannot get that this functional goes to 0 uniformly. But now, since this is a compact, for these infinite many vectors, we can have finite many, and all others are epsilon close to this finite many. So then that will work, okay? That will make the functional go to 0 uniformly. So that is the idea, okay? So now let's look at this proof, y1 through ym, such that a ball of x is included in y in script y, norm y minus yj, less than epsilon, excuse me, less than epsilon. So since ynk star goes to y star in weak star topology, there is a k greater than or equal to 1, such that yj, y is the n of k, y star minus y star, this inner product notation absolute value is less than epsilon. For j is less than or equal to m, and k greater than or equal to big K. Now here, let's look at this again, the reasoning, okay. In order to show that our desired norm go to 0, we would like to see that this functional applied to a general vector in the ball would go to 0 uniformly. If it is finite and many, then since for each one it goes to 0, then for finite and many it goes to 0 uniformly. But the difficulty is that we have infinite many vectors in the ball of y. So since our operator A is a compact, we can choose finitely many, such yj, and all others are close to it. So this is the idea, to use compactness of A to prove compactness of A star. Okay. So this is true for j from 1 to m, k is greater than or equal to k. And again, let me say it again. This is, for each yj, we can find the big K for this to work. Since we have finitely many yj, we just choose the greatest such K. So this works, this big K works for all j from 1 to m. Yeah. So it works for finitely many, because if you have finitely many numbers, you can find the largest one. Okay, let x be an arbitrary element in ball x and choose yj such that norm ax minus yj is less than epsilon. This is possible to choose such a yj. It is because of that, okay. So every vector of the form ax is in one of this set. So you have one of yj to make this less than epsilon. So we can choose yj such that ax minus yj is less than epsilon for k less than epsilon. Then for k greater than or equal to big K, we want to see that this is uniformly small. The way to see it is to separate this into two parts. Separate this into two parts. One part is AK minus YJ. The other part is YJ. Okay. Now, each of these two terms is small, but due to different reasons. This term is small because this norm is less than epsilon. That means this vector is small. So this inner product notation, this coupling is small. And this one is small because of this. This is less than epsilon for all j from 1 to m and k greater than or equal to k. So, okay, this one is less than 2 times the norm of this. Yeah, because this 2 is the upper bound for the norm of this vector, because this is as the norm of this one is at most 1, and the norm of this is at most 1. So the norm of this is at most 2. So times the norm of this, okay, plus epsilon. This one is less than epsilon because of this. So, but this is also less than epsilon. So the whole thing is less than 3 epsilon. So that's A star YNK star minus A star YNK star is less than or equal to 3 epsilon. I should say less than or equal to 3 epsilon. Okay. For k greater than or equal to k. So see, we have 3 epsilon here. That is the same as epsilon. So this says that this norm goes to 0. So that is the proof of the first part. Okay, the first part is that A is compact, then A star is compact. Now we are going to prove the converse. For the converse, assume A star is compact. Then by the first half of the proof, since this is compact, so it's dual, A double star is compact. Then if A double star is compact, we know that X is a subspace of X double star. So when this operator restricts to X, you get A. Since this is compact, we can check its restriction is also compact, because A of this ball in X is a subset of A star double star of the ball. So we can check that since this A star double star is compact, A is compact. The reasoning for this part is a kind of definition tracing. Takes some time to say it clearly, but there's nothing deep here. So we say it is easy to check. So the theorem has been proved. Now, for Banach space is xy, let B sub 0 of xy denote the set of all compact operators from x to y, and let B0 of x equals this. That means if the operator is from X to the same space X, we can write it in just one X. Okay. So then this B0 of XY is a closed linear subspace of that. So of course, this is a linear subspace of that because the compact operator is a linear subspace. What does this mean? This means the sum of two compact operators is compact, and multiplication by a number makes a compact operator go into the compact operator. Okay, so this, but the crucial word here is the word closed. Okay. This means that if you have a sequence of compact operators converging to an operator, then the limit operator is also compact. And the proof of this assertion is similar to that of proposition 242b for Hilbert spaces. So now let B sub double zero xy denote the set of all bounded operators for which range T is finite dimensional. Okay, such operators are called operators of finite rank. So B double zero denotes the set of operators of finite rank. So if we have the same space X, we just write X once. If Y is a Hilbert space, then B double zero XY is dense in B0 of XY. And the proof, this is C theorem 244C. And in the proof, we can see that the proof depends on the fact that we have, when we have separable Hilbert space, okay, no, you know that if Y is, if X is, if Y is a Hilbert space, if this operator is compact, then we can show that the range is a separable Hilbert space. The range is a separable, the closure of the range is a separable Hilbert space. It's separable because the image of the unit ball, we have an epsilon net, we call that epsilon net. It's totally bounded, so it has an epsilon net for every epsilon. You take these points, find many points for each epsilon, you take these points together, you get a countable dense subset. So the close of the range is a separable Hilbert space. And for this separable Hilbert space, we can find an orthonormal base. Then we can have standard projection Pn to project that is orthogonal projection onto the first n vectors in the basis. And our proof depends on the existence of such orthonormal basis. So the proof does not work for Banach spaces. So there is a separable reflexive Banach space X for which B00X is not dense in B0X. And before this was discovered, people spent a lot of time to find out whether for every Banach spaces, B00X is dense in B0X. So then in 1972, this person discovered that there exists a separable reflexive Banach space X for which this is B double zero X is not dense in zero X. So this question was answered in 1972. Now we are going to prove that for a compact space X, for this C of X, this is a Banach space, okay? The compact topological space, again, when we say compact space, we mean compact Hausdorff space, okay? So B double zero C of X is dense in B0 of C of X. So now we are going to prove this. We are going to do this next time.